and it has the Tarsis surface expression is maybe the most prominent expression on the surface of Mars, with the large volcanoes, including Olympus Mons. And then you have the Martian northern lowlands that many people believe are the result of an ocean that has covered the northern, a large part of the northern hemisphere of Mars in ancient times, although there is no consensus on that yet. At the poles we have the ice caps. We have the North Polar ice caps with this strange swirling pattern here that people don't understand well yet. The size of this ice cap is about half the size of the Greenland ice cap, and it's about similar in thickness, 3 kilometers maximum. And in the south we have the much smaller South Polar ice cap, which was for a long time believed to be made mainly of CO2 ice, but opinion is now shifting towards that one also being H2O ice for various reasons. Now, just a brief timeline of the observations and discoveries. Up to 32 years ago, we knew next to nothing about Mars, and then you can say that the surface of Mars was discovered in these decades 71 to 1980, when we got the photos from the Mariner orbiters and the Viking orbiters, and then there was this detailed search for life in the Martian soil by the Viking landers, turning out negative. 93, there was the Mars Observer sent off, but contact was lost upon arrival at Mars. And then some of the experiments on board that orbiter have been flown on later missions, including Mars Global Surveyor, which is still sending back pictures from the surface of Mars, having been in operation for 6-7 years now. The Mars Orbiter camera takes these photos of the gullies and other things with a resolution down to 1 meter per pixel, which is much better than the Mariners and the Vikings could deliver 20-30 years ago. Then there's the laser altimetry producing this detailed map of the surface of Mars. And then there was a setback in 1999 with the loss of Climate Orbiter and Polar Lander, but since then everything has been going fine with Mars Odyssey mapping the ground ice, and the European mission Mars Express sending back pictures. That's an orbiter, and the Beagle lander did not make it safely to the surface of Mars, but I'm sure they will try again. And then the Americans have the Mars exploration rovers now going on the surface. And the bottom line, of course, or the sort of main purpose of the current Mars exploration programs is to follow the water, as they call it, the Americans at least, because looking for water means looking for possibilities for life to thrive nowadays, or having thriven on the surface of Mars at some time in the distant past. And we now know that, as everybody knows, I'm sure, we cannot have liquid water stable on the surface of Mars at present due to very, very low temperatures. This is the average surface temperature on Mars, averaged of the whole year and the whole planet, happens to be the same as the average annual temperature of the coldest place on Earth, the very coldest locations in Antarctica, 958. And these are the minimum and maximum temperatures, and the pressure is so low, just about 6-7 millibars usually, that we cannot have water in stable form, even though we would have temperatures above the freezing point. And put the bowl out, it will, in most cases, freeze right away, but could happen that temperatures are higher than zero, but then it will evaporate because of the very low pressure. The atmosphere is mainly made of CO2, and we have these polar ice caps made of H2O ice, and we have abundant snowfall in winter, CO2 blanket 1-2 meter thick, covering the poles, but evaporating away rapidly in springtime in each hemisphere. We have layered deposits beneath the ice caps in both hemispheres, both polar regions, several kilometers thick, and these are, the layering shows up as different colors. There is a darkish layer with a lot of dust in the ice, alternating with a whiter layer with less dust. This testifies to great climate changes that have occurred in millions, tens of millions of years back in time, and they are believed to be due to obliquity variations which are quite large on Mars. The inclination of the axis, which is presently 25 degrees, varies between 55 and 0, which is much greater than the variations of the Earth's axis. Now, geologists working on Earth, they have this good old saying that the present is the key to the past. But if they had started out doing geology on Mars, they would probably not have come up with this same saying, because present processes of Mars are not really that similar to what has happened to us in the distant past. There is definite evidence from that already came out from the Mariner and Viking photos, showing that large amounts of water have flowed on the Martian surface in the distant past, 3 billion years ago or more. And those who are experts in this, they talk about two different kinds of formations. About the outflow channels, shown here in red, sort of emanating from equatorial regions and mainly flowing up to the north. This is the most sort of prominent region here. And then they talk about the so-called valley networks, which are mainly prominent in the southern highlands. Now, what are these? Here is one example of such an outflow channel. These are huge channels testifying to very, very large amounts of water that have flown catastrophically, it seems, in the past. This is the flow direction here, and you can see these streamlined features, sometimes called teardrop features, that testify to water erosion quite clearly. And the points where these flows originate, they seem to indicate that this has occurred catastrophically. And here is a close-up of this region here. They emanate from sort of single locations, of course, large places, but still something has just started off there and just in that direction. And this they call chaotic terrain. It's just like the whole surface has slumped down, and when the water got off, and just leaving this chaotic jumble here. So what has happened? Well, here's another example of these beautiful teardrop-shaped islands formed by the water erosion. What has happened? There are of course different theories. People don't agree, but the sort of leading theory, look at just this one here before you look at the picture, is that there has been some dramatic release of groundwater from confined aquifers, water-bearing layers in the ground, when some kind of permafrost seed was ruptured. Of course, not everybody agrees on this. Some people talk about volcanic heating leading to this sudden melting of ground ice. Some people talk about cometary impacts doing this. Some people talk about possible subglacial lake. Maybe there was a snowball Mars sometime in the future or whatever. But anyway, and then the valley networks, which were shown in yellow here on this map. Here's one example of those. This is kind of a very well-defined valley here. And sometimes the network, so-called, is more prominent than seen in this picture. This one has actually very few tributaries, but some of them have more tributaries than this one here. But actually the fact that there is a lack of a well-defined tributary network, even though they call them networks, they tend to want to explain this not as a result of surface flow or surface precipitation, but what they call sapping or collapse of surface layers due to weakening of underlying soil by groundwater flow. So also some subsurface processes may be responsible for this. So this was how it stood when Mars Global Surveyor went in orbit around Mars in the late 90s. And they have this much better camera than the previous orbiters. And then in 2000, there is this announcement of recent groundwater seepage and surface runoff on Mars. So not 3 billion years ago, but something that, well, they were pretty vague about that in the paper, but something maybe as recent as a few decades ago, or maybe as distant in the past as a billion years ago, something like that. So definitely much more recent than the old channels systems. And these so-called gullies that are found in sort of cliff sides and crater walls have usually 3 different sort of characteristics, or 3 First, the so-called alcove. There is a kind of a collapse here, or erosion, because of some undermining of the material here in the cliff, forming a theater-shaped depression by collapse. And there is material that is collapsing down. It has been channeled into a very well-defined channel, incised into the debris apron on the slopes here, and often, or usually very, very fresh looking. That's one of the arguments for this being really young. And the width of this is something like a meter or 10 tenths of meters or something like that. And then the material that goes down through the channel, of course, is deposited in the lowest part of the slope, forming often a very clear debris apron. Sometimes there are several channels and several aprons sort of overlapping each other. A few examples here. Gorgon chaos. Here are many gullies starting at a well-defined layer here in this cliff here, about 100 meters below the surface here. Here is a so-called south-polar pit, probably different sort of bedrock material here than here. Equally well-defined gullies here, V-shaped, and they're sort of narrowing downward into the talus slope. And you can see that the effect of the erosion through this gully erosion is to sort of erode this whole escarpment here, and forming what they call badlands. Newton Basin, here is like a rocky outcrop, several small gullies going here down into this talus slope here, and disappearing kind of into it. And here is an example showing that there can be snow in these pictures, CO2, snow mainly, but also some H2O snow mixed in with it. But that does not mean that the snow, or mesting of the snow, forms the gully features, because this stuff mainly or solely evaporates away, sublimates up. But of course, there are some people who are claiming that gullies can be explained by snow mesting. But the leading hypothesis put forward by Malin and Paget, I believe it's still the leading hypothesis, although there are other ideas coming up, is that there is an underground aquifer or water-bearing layer where liquid water can exist, perhaps due to geothermal heating. And even though there is not a lot of heating, the water can still stay in liquid form if it has a lot of dissolved salts in it, briny composition, keeping it maybe fluid down to minus 50 degrees Celsius and so on. And then the water in this layer is coming out here, and then it finds a hillside, and it wants, of course, to seep out and down the slope into the soil here, or loose talus. But obviously the cold won't let it, and it freezes right away, or very soon, forming an ice barrier here, which won't let the water out. Pressure builds up until the barrier breaks. Water gushes out, mixes with the soil here, forms a slurry of debris and water and ice that rushes downward in a sudden event, forming one of these gully channels. Then it freezes again, and the process repeats itself over and over again. And forming these gullies over time. Not sure if they claim that one gully channel is formed in one event, or if you need many of these events to form a gully, but these are initial ideas. Alternative hypotheses are melting of ground ice in the top few meters of the soil. We now know that there is ice in the top few meters of the soil, definitely, from the Mars Odyssey results, gamma ray spectrometry, and melting of superficial snow under different climatic conditions. When you have the higher obliquity, higher temperatures in the polar regions, I forgot to say that these gullies are, the majority of them seem to be facing the polar regions. That means that they are not facing the sunlight, usually. And that means that there's greater likelihood for this ice plug forming, because the sun won't melt it. But then you can have the possibility of higher obliquity, and then more sunlight, and then you can even increase the atmospheric pressure under those conditions, and then you can even have liquid water forming by melting of superficial snow, H2O snow. There are also some ideas about the sudden discharge of buried liquid CO2 kept pressurized beneath the Martian surface. Okay. So terrestrial analogs can provide some insight into this. We have a situation that we have these wonderful maps of the surface of Mars, and we have beautiful photographic coverage. We know the surface of Mars better than we know the surface of the Earth, but we can't go there to take a detailed look. So we can go to places on our own planet and compare. What do we see there? We see some similar features. People have looked at gullies at polar conditions on Earth. The temperature is definitely, average annual temperature is definitely below zero, way below zero. And studies there indicate that soil saturation by snowmelt and ice melt initiates debris flows that form gullies. We're talking about something like a slurry that has 10 to 30% water content, and mainly it's debris just sliding down the slope to form a gully. Iceland has maritime climate, lots of rain, no polar conditions, but strong geological similarities with Mars, some of which are mentioned here. We have sites of catastrophic flooding, and we have flood basalts and pseudo-craters, and we have lots of examples of circulation volcanism and circulation lakes. The country is sitting astride the mid-Atlantic ridge running through here, and that defines the geology of Iceland. These are the regions that set out in color that have been, where volcanism has been active over the past 10,000 years. It was also active prior to that, then the country was ice covered, and then you have a lot of the formation of a lot of mountains, ridges, and tuyas that are formed in circulation eruptions. So when you go out to check gullies in Iceland, compare them with the Martian ones, it's good to take a look both at the tertiary plateau basalts, which are quite similar to the basaltic regions on Mars, with layer upon layer upon layer of tertiary lava flows, 3 to 10 million years ago or so. And then you can also take a look at these Pleistocene hieroclastites formed during the Ice Age by basaltic eruptions beneath the ice. Water melts the ice, comes to the magma melts the ice, comes into contact with meltwater, and cools very rapidly, goes to crystallize, forms a sort of a rubble that takes on a brownish color when it undergoes alteration later on. That's what we call moldbreak in Iceland. So what do we see when we look at the hillsides in Icelandic mountains? This is from a tertiary basalt region here. This is the typical situation on Mars here. Here's the cliff. Here are the gullies coming from the lower base of the cliff down into the talus slope. Here is a tertiary basalt pile in Iceland, and you have some cliffs seemingly starting from the lower base. Sorry, gullies starting from the lower base of the cliffs, going down the talus. But there is also definitely examples of water seemingly coming from the top plateau, going down the cliffs, and then continuing down there. So this is not the ideal comparison with the Martian caves, where it seems to be coming out of the wall between layers here, but not from the surface. Here's another photo from Iceland, Asia Basalt Plateau, close to Reykjavik. This one seems to be starting up here on the plateau, continuing down here. There are some that seem to be starting at these base of these outcrops here, up here, and there are some gullies that even seem to be starting on the talus slope itself, just coming out there. And actually we have sometimes witnessed in heavy rain of the sea water coming out everywhere, coming down everywhere, coming out here on the middle of the slope, emerging here and coming all the way from the top of the plateau. What do they look like in close-up, those gullies? You can see them in quite many places. A few meters wide here, these levees on the sides here, quite clear, and then the material that has been slumping down here is forming a kind of an apron down here like this. When we looked at the number of photos from Mars and Iceland and compared them, and we start to get a feeling for a possible classification, which is not meant to be all-encompassing, but kind of a first attempt to come to grips with what we are seeing. Just briefly, first we start with this, no gullies at all, cliff and talus. Initial gully formation here, and advanced gully formation forming these wedges here, with the V-shaped wedges, with the pointing upward like this, and then a very advanced stage where we have a wide alcove up here and another one up here, and coalescing the brief hands at the base. And legs. Yeah, okay. So here are examples of these four stages from both Mars and Iceland. No gullies at all here, just a cliff and a talus. Basaltic tile here, no gullies at all. Stage 2, initial gully formation. This is on Mars here. Gullies starting to form in the talus. This is on Iceland here. Here is an outcrop, and there are some gullies starting to form beneath it, but of course you can see that there are some starting points up here, so maybe it's not all that convincing. And stage 3, this wedge formation here, when it's talus is becoming quite heavily eroded. This is on Mars here. You can see these V-shaped wedges here. This is Iceland. Here is a V-shaped wedge, and even clearer here in Asia. And stage 4, cliff face erosion, talus slope destruction. On Mars here, here's a large alcove and something comparable in Iceland here. In conclusion, our main conclusions from preliminary gully studies in Iceland are that they are almost certainly not formed by water emerging from underground aquifers. We see small seeps of water coming out between the basaltic layers, but they are not more than that. The typical sort of discharge that we would need to form a Martian gully is like some thousands of cubic meters over a few minutes or so. And what we see in Iceland coming out in the basalt pile is nothing comparable to that. The snow left in the spring and the rain all year round, more or less, delivers enough water in Iceland to form these gullies. Often run off from the top of the plateau or the mountain. The top of the talus slope can become water saturated in Iceland, initiating debris flow starting at the base of the cliff. That is analogous to Mars, although the origin of the water is not the same, but it starts at the same place on the talus. And then we have this sort of initial attempt to classify different gully systems into different evolutionary stages, but one can of course question how realistic that is. So thank you very much.
One short question.